This chapter discusses physical database organization. It is based upon her book, Principles of Database Management, published by Cambridge University Press. You can find more information about her book on the website at the bottom of my slide. My name is Bart Bausens, and I'm one of the authors of the book. This chapter deals with physical database organization in its broadest sense. A primary focus is on physical database design, the translation of a logical data model into an internal data model, including the design of indexes to speed up data access. We also zoom out to other concerns of physical data storage, such as enterprise storage subsystems, as well as the important area of business continuity. Physical database organization focuses on conceiving the internal data model. The following sections aim at providing an overview of some widely applied principles with respect to physical database design and the impact of certain design decisions on performance. We focus on tablespaces, index design, different possible access paths given particular properties of queries, tables and indexes, and different ways of efficiently implementing joint queries. In its most simple incarnation, a physical user database is a collection of index files and data files organized according to the principles on record organization and file organization. However, many DBMS implementations introduce an additional level of indirection between a logical database and the physical data files, called a tablespace. A tablespace can be considered as a physical container of database objects. It consists of one or more physical files, often with the option of distributing the files over multiple storage devices. In smaller scale database systems, the files are managed by the operating system's file system, whereas high-performance DBMSs often manage the files themselves. Every logical table is assigned to a tablespace to be persisted physically. We then speak of a stored table. A stored table occupies one or more disk blocks or pages in the tablespace. A tablespace can contain indexes as well, although sometimes separate index spaces are used for this purpose. The use of tablespaces provides the first important instrument to the database administrator to tune the DBMS's performance. For example, data from the same table can be distributed over multiple storage devices. Different subsets of the data can then be searched in parallel in the context of a single complex query for improved performance. We call this intra-query parallelism. On the other hand, it can also be desirable to avoid involving multiple storage devices in the same query and to rather optimize the system for inter-query parallelism, where many simple queries can be executed in parallel. It is also possible to cluster data from multiple tables into a single tablespace to cater for efficient retrieval of strongly interrelated data. Physical database design comes down to attributing logical concepts to physical constructs. This is a joint responsibility of the database designer and the database administrator. You can see this illustrated here. Most contemporary DBMSs are equipped with extensive performance tuning facilities. These pertain to decisions with respect to distributing data and tables over storage media, detecting and resolving I/O problems of storage devices, providing index tuning wizards to monitor and optimize the use of indexes, monitoring and optimizing the access paths involved in query execution, etc. Even though most DBMSs provide ample auto-configuring and self-tuning features, this responsibility remains to a very large extent with the database administrator. The number of parameters that can be manipulated by the latter is often very extensive. Indexes are probably the most important tuning instrument to the database designer and database administrator. The below table summarizes the respective index types discussed before. The main reasons for index creation are the following: efficient retrieval of rows according to certain queries or selection criteria. An index can be created on any column or combination of columns in a table. Efficient performance of join queries. The join is one of the most expensive operations performance-wise in query execution. Indexes can be used to perform the search for related tuples in both tables in a more efficient way. Enforce uniqueness on a column value or combination of column values. It would be very inefficient for a DBMS to enforce a uniqueness constraint on an attribute type or set of attribute types without using an index. Logical ordering of rows in a table. Every index is ordered in a certain way according to the attribute type or attribute types it involves. As such, the index also specifies a logical ordering on the actual tuples in a table, which contain, amongst others, these same attribute types. Finally, physical ordering of rows in a table. The ordering of the index entries can also be used to determine the physical order of the rows in a stored table. In that case, the values to the index search key or index's search keys determine the physical positioning of the respective rows on disk. If every value or combination of values in the search key is unique, we have a primary index. Otherwise, it's a clustered index. Since indexes belong to the internal data model, which is not part of the most recent versions of the SQL standard, there is no standard SQL syntax for index creation. Still, most DBMSs use a similar syntax, which is illustrated here. The unique and cluster clauses are optional. Here you see some examples. The first example creates a unique index on product number, which is the primary key. The second example creates an index on product price and product type. The third example creates a clustered index on product name. The final example illustrates an index on the foreign key supplier number in the product table. Apart from a single primary or clustered index for every table, one can define as many secondary indexes as desired. However, every index also comes with a cost. It consumes storage capacity and may slow down update queries, as the corresponding indexes need to be updated as well. The database administrator must rely on statistical information in the catalog, as well as his or her own experience to decide which indexes to create. Fortunately, because of the physical data independence, indexes can be added or deleted in light of altered requirements or new insights into data usage, without affecting the logical data model or applications. In addition, secondary indexes can be constructed or removed without affecting the actual data files. This is not the case for primary indexes, and clustered indexes. In what follows, we zoom in on database access methods. We discuss the functioning of the query optimizer, index search, multiple index and multi-column index search, index-only access, and full table scan. SQL is a declarative query language in which a developer specifies which data is required, but not how the data is to be located and retrieved from the physical database files. In many cases, different access paths exist to get to the same data, although the time to accomplish the retrieval task may vary greatly. For each query, it is the responsibility of the optimizer to translate the different possible ways of resolving the query into different access plans and to select the plan with the highest estimated efficiency. Modern cost-based optimizers calculate the optimal access plan according to a set of built-in cost formulas, as well as information such as the table or tables involved in the query, the available indexes, the statistical properties of the data in the tables, etc. The optimizer uses heuristics to determine the best access plan possible, based on the available information and within the boundaries of calculation time. The query processor is the DBMS component that assists in the execution of both retrieval and update queries. It consists of a DML compiler, a query parser, a query rewriter, a query optimizer, and a query executor. The DBMS maintains the following statistical data in its catalog to be used by the optimizer to calculate the optimal access plan. Table-related data, such as number of rows, number of disk blocks occupied by the table, and number of overflow records associated with the table. Column-related data, such as number of different column values and statistical distribution of the column values. Index-related data, such as number of different values for index search keys and for individual attribute types of composite search keys, number of disk blocks occupied by the index, and index type such as primary, clustered, or secondary. And finally, tablespace related data, such as number and size of tables in the tablespace, device-specific I/O properties of the device on which the table resides. The first important concept is the filter factor, or FF in short. A filter factor is associated with a query predicate. The query predicate specifies a selection condition with respect to a particular attribute type AI in the query, such as customer ID equals 11,349, or gender equals M, or year of birth is bigger than or equal to 1970. The FFI of a query predicate represents the fraction of the total number of rows that is expected to satisfy the predicate associated with attribute type AI. In other words, the filter factor denotes the chance that a particular row will be selected according to the query predicate. For queries over a single table, the expected query cardinality, QC, or the number of rows selected by the query, equals the table cardinality, TC, or the number of rows in the table, multiplied by the product of the filter factors of the respective search predicates in the query. In other words, QC equals TC times FF1 times FF2 up to FFN. If no further statistical information is available, then an estimate for FFI is 1 divided by NVI, with NVI representing the number of different values of attribute type AI. For example, suppose a customer table contains 10,000 customers. Let's examine the following query. Select customer ID from customer table where country equals UK and gender equals M. The TC equals 10,000 as there are 10,000 rows in the table. Suppose a table contains 20 different countries and gender has two values M and F. In that case, FF country equals 0.05 and FF gender equals 0.5. The expected query cardinality can then be calculated as QC equals 10,000 times 0.05 times 0.5 equals 250. Thus, we expect 250 rows in a data file to have both the properties country equals UK and gender equals M. Let's first examine the situation with a single query predicate, where the query involves a search key with only a single attribute type. If an index exists for this attribute type, an index search is usually the most efficient way of implementing the query. This approach is applicable to queries targeting a single value as well as range queries. Let's assume a B+3 index is available as shown below. We assume the following range query. Select star from my table where my key is bigger than or equal to 12 and my key is less than or equal to 24. The index allows filtering which data rows should be retrieved, hence avoiding unnecessary retrievals and therefore greatly improving performance or query execution. The following steps are taken as illustrated in the figure. Starting from the index's root node, descend the B+tree along the tree pointers according to the search key values onto the first leaf node that contains key values satisfying the search condition. From this leaf node, follow the data pointers to retrieve the data rows satisfying the search key values. Follow the next three pointers in the leaf nodes to subsequently access all nodes that contain key values still within the desired range of the search key. For each of these nodes, follow the data pointers to retrieve the corresponding data rows. If the query involves a single search key value and not a range of values, an efficient alternative would be to organize the table according to the random file organization method, mapping search key values onto physical locations by means of hashing instead of using an index. Note that this approach is not efficient in supporting range queries, where an interval of key values is used as a search criterion. As to range queries, a primary or clustered index is even more efficient than a secondary index. Indeed, if the data records are stored in the same order as the search key, the B+tree's leaf nodes can be accessed by means of the next pointers and the data rows can be retrieved in the same order by means of sequential block accesses. On the other hand, applying the same procedure by means of a secondary index would result in all random block accesses on the data file jumping back and forth because the data records are not in the appropriate physical order. This is illustrated in a figure. In such case, the DBMS would probably first sort the pointers to the disk blocks to be accessed according to their physical address, but this sorting also induces a certain amount of overhead. If the search key is composite, a similar approach is feasible, but other options exist as well, depending on the availability of single column and/or multi-column indexes, which cover all or part of the attribute types that occur in the query predicates. If the index attribute types are the same as the attribute types in the search key, then the approach in the previous section is usually the most efficient. The multi-column index then allows filtering out and retrieving only these data rows that satisfy the query. In most cases, it is not feasible to create a multi-column index for every possible combination of search keys, as these indexes would become very large. For example, a search key with 5 attribute types, each with 10 possible values, would yield a multi-column index with 100,000 entries. When using single-column indexes instead, there would be 5 indexes, each with 10 entries, thus 50 entries in total. The case becomes even more complex if not only queries are executed involving all search attribute types, but also queries involving an arbitrary subset of these attribute types. To efficiently support these kinds of queries, a multi-column index should have all attribute types involved in the query predicates in its leftmost columns. To cater for all possible search keys with n attribute types or less, the number of combinations of the ceiling of n divided by 2 out of n indexes are required. For example, with 3 attribute types, the number of combinations of 2 out of 3 or 3 indexes are required. The index combinations A1, A2, A3, A2, A3, A1, and A3, A1, A2 accommodate for any query that includes A1, A2, and or A3. A few cases are illustrated below. A query involving A1, A2, and A3, any index can be used for that. A query involving A1 and A3, use the index A3, A1, A2. A query involving A2 and A3, use A2, A3, A1. And a query involving only A1, use A1, A2, A3. Multi-column indexes are only appropriate for selective cases, such as queries that are executed very often or that are very time-critical. An efficient alternative is to use multiple single-column indexes or indexes with fewer columns. If we have a query of the following format, select star from my table where A1 equals value 1 and A2 equals value 2 and so on until AN equals value n. And we have single column indexes for every attribute type AI, then the intersection can be taken between the sets of pointers in the index entries that correspond to the desired values of AI. This intersection yields the pointers to all records that satisfy the query. In case the predicates are combined using OR, the union of the sets of pointers needs to be considered. As an example, this figure illustrates the use of 2 indexes, one on country and one on gender, to execute the already familiar query. Select customer ID from customer table where country equals UK and gender equals M. By taking the intersection between the set of pointers referring to people living in the UK and the set of pointers referring to males, all pointers to males living in the UK can be identified. For queries with many predicates, a multi-column index over all these predicates is the most efficient alternative. Its filter factor is equal to the query's filter factor, so only the data rows that satisfy the query are retrieved. Still, this approach becomes unfeasible if many attribute types are used in query predicates, as the indexes would become very large and possibly redundancy is required to accommodate for queries with predicates for only a subset of the attribute types. As an alternative, multiple indexes can be combined to cover as many query predicates as possible. This requires more indexes, but with a much lower total number of index entries than in the case of a composite index. Generally speaking, the more selective a query predicate's filter factor, the more desirable it is to use the index on the corresponding attribute type in the access plan. If the filter factors associated with non-indexed attribute types are in their turn very selective, many records are retrieved in vain, which is inefficient. Ultimately, the number of block accesses determines the performance, not the number of rows retrieved. Thus, the impact of clustering always needs to be investigated, since despite what the filter factors indicate, using a primary index or a clustered index may be more efficient than using a secondary index, especially for range queries. In some cases, the optimizer might be extremely lucky in the sense that the query can be executed entirely without accessing the data files based solely on information in the index. In that case, not only the attribute types used in a search key should be indexed, but also the attribute types that occur in the query select clause. For example, consider the following query. Select last name from customer table where country equals UK and gender equals M. If there exists a multi-column index or a combination of single-column indexes over the attribute types last name, country, and gender, then the data in the index or indexes suffices to yield the query result. In that case, access to the actual data rows can be avoided. This is especially efficient if the data rows consist of many attribute types and take much more time to retrieve than index entries. Index-only access is thus an additional reason for creating multi-column indexes. Of course, the more attribute types are included in the index, the higher the negative performance impact is on update queries, since the index entries need to be updated as well. Note that, because the data rows are not retrieved anyway, a primary or clustered index does not yield better performance than a secondary index for index-only access. If no index is available for the attribute type or attribute types and tables or tables involved in the query, there is no other option than to linearly search the entire table for rows that satisfy the query. For very small tables, or for queries that require nearly all of a table's tuples anyway, a full table scan might actually be more efficient than using an index. However, the higher the query's filter factor and/or the larger the table, the less efficient a full table scan will be. In what follows, we zoom in on join implementations. We start with a recap and then discuss nested loop join, sort merge join, and hash join. One of the key differences between database organization and just file organization is the fact that database organization should also cater for queries that involve multiple tables by means of a join construct in SQL. A join query between two tables specifies selection criteria that relate tuples from the two tables to one another according to a so-called join operator. It is one of the most time-consuming operations in an RDBMS and therefore deserves special attention. We restrict ourselves to the inner join. The general notation of an inner join between tables R and S is shown here. The theta operator specifies the join condition, which are the criteria that determine which rows from table R are combined with which rows from table S. You can see a join between tables R and S illustrated here. With a nested loop join, one of the tables is denoted as the inner table and the other becomes the outer table. For every row in the outer table, all rows of the inner table are retrieved and compared to the current row of the outer table. If the join condition is satisfied, both rows are joined and put in an output buffer. The inner table is traversed as many times as there are rows in the outer table. Therefore, this approach is mainly effective if the inner table is very small or if the internal data model provides facilities for efficient access to the inner table, such as by means of a primary or clustered index over the joined columns of the inner table. This approach is also more efficient if the filter factor of the other query predicates is very restrictive with respect to the rows that qualify in the inner table. You can see the algorithm outlined here. With a sort merge join, the tuples in both tables are first sorted according to the attribute types involved in the join condition. Both tables are then traversed in this order, with the rows that satisfy the join condition being combined and put in an output buffer. In contrast to a nested loop join, every table is traversed only once. This approach is appropriate if many rows in both tables satisfy the query predicates and/or if there exist no indexes over the joined columns. The sorting algorithm that is applied in stage 1 may be quite time-consuming. Hence, a sort merge join will be more efficient if the tuples in R and/or S are already physically ordered in the stored tables according to the attribute types used in the join condition. You can see the algorithm outlined here. Finally, with a hash join, a hashing algorithm is applied to the values of the attribute types involved in the join condition for table R. Based on the resulting hash values, the corresponding rows are assigned to buckets in a hash file. The same hashing algorithm is then applied to the join attribute types of the second table S. If a hash value for S refers to a non-empty bucket in the hash file, the corresponding rows of R and S are compared according to the join condition. If the join condition is satisfied, the rows of R and S are joined and put in the output buffer. Still, given the possibility of collisions, rows with different column values may still be assigned to the same bucket, so not all rows assigned to the same bucket will necessarily satisfy the join condition. The performance of this approach depends on the size of the hash file. If, instead of a physical file, the hash structure can be maintained entirely in internal memory, a hash join can be very efficient. We continue this chapter on physical database organization by returning to the storage hardware. We focus on the broader aspect of pooling individual devices and managing them as a so-called enterprise storage subsystem. First, we discuss disk arrays and RAID as a mechanism of combining multiple physical devices into a single, larger logical device. Then, we deal with network storage techniques such as SAN and NAS. We conclude the chapter with a discussion on how these techniques can be applied in the context of business continuity, which is a primary concern to most organizations. Whereas the storage capacity of hard disk drives has increased tremendously over the last 2 decades, their performance has not increased at the same rate. Consequently, it is often more efficient to combine multiple smaller physical disk drives into one larger logical drive. The reason is twofold. First, distributing data over multiple physical drives allows for parallel retrieval, resulting in much improved performance. Second, each additional drive increases the risk of failure, but if a certain measure of data redundancy is introduced, this risk can be mitigated and the reliability actually becomes much better than with a single physical drive. Both considerations are at the core of the redundant array of independent disks or RAID concept. RAID is a technology in which standard hard disk drives are coupled to a dedicated hard disk controller, the RAID controller, to make them appear as a single logical drive. The same can be realized by a software RAID controller without dedicated hardware, but in that case, the performance increase is slower. The following techniques are applied in RAID. Data striping. Subsets of a data file, called strips, are distributed over multiple disks to be read and written in parallel. The strips can consist of individual bits or entire disk blocks. With n disks, bit or block I is written to disk I mod n plus 1. Remember, mod represents modulo, or remainder after integer division. With bit-level data striping, a byte is split into 8 individual bits to be distributed over the available disks. For example, 4 disks each contain 2 bits of the same byte. Disk 1 contains bit 1 and 5, disk 2 contains bit 2 and 6, etc. In that case, every disk participates in every read-write operation. The number of disk accesses per unit of time remains the same, but the number of bits retrieved in a single access increases with a factor equal to the number of disks, resulting in higher transfer rates for a single transfer. With block-level data striping, each block is stored in its entirety on a single disk, but the respective blocks of the same file are distributed over the disks. In this way, individual block accesses remain independent. Efficiency of a single block access is not increased, but different processes can read blocks in parallel from the same logical disk, hence reducing the queuing time. Also, a single large process can read multiple blocks in parallel, hence reducing the total transfer time. Redundancy. Redundant data is stored along with the original data to increase reliability. The redundant data consists of error detection and correcting codes such as Hamming codes or parity bits. Disk mirroring. This is an extreme form of redundancy where for each disk there is an exact copy called the mirror containing the same data. Note that if the probability of a single disk failure is p, probability of one of n disks in a RAID setup failing is n times as high. However, when mirroring the disks, the chance of both copies failing is p squared, which is much lower than p. On the downside, mirroring consumes much more storage space than the error correcting codes. There exist multiple RAID configurations called RAID levels. The term level here is somewhat misleading, as a higher level not necessarily implies a better level. The level should just be considered as different configurations with a different combination of the above-mentioned techniques, resulting in different characteristics in terms of performance and reliability. We summarize the properties of the respective original RAID levels in this table. RAID level 0, block level striping, no error connection, and improved read and write performance due to parallelism. In other words, multiple processes can read individual blocks in parallel. RAID level 1, disk mirroring, error correction due to complete duplication of data. Improved read performance, Both disks can be accessed by different processes in parallel. Write performance is slightly worse, since data needs to be written twice. RAID level 2. Bit level striping with separate checksum disk. Error correction happens through Hamming codes. Improved read performance through parallelism, but slower write performance. Calculation of checksum disk involved in every write may become a bottleneck. RAID level 3. Bit level striping with parity bits on separate parity disk. Error correction through these parity bits. Improved read performance through parallelism, especially for large sequential transfers. However, slower write performance, less calculation overhead than with RAID level 2. But the parity disk involved in every write may still become a bottleneck. RAID level 4. Block level striping with parity bits again on separate parity disk. Error correction happens through parity bits. No improved read performance for individual block, but support for efficient parallel block access. Slower write performance. See also RAID 3. And finally, RAID 5, block level striping with distributed parity bits. Error correction through parity bits. For read performance, see RAID level 4. However, better write performance than RAID level 4, since the parity bits distributed over data disks, so no parity drive as a bottleneck. Some typical RAID levels are illustrated in this figure. The letters represent blocks. The combinations of letters and numbers represent bits in a block. The colored disks or disk sections denote redundancy. RAID level 0 is used if performance is more important than fault tolerance. RAID level 1 is mostly used for very critical data, for example the log file of the DBMS. This configuration is the best in terms of continuity, as there is always an exact copy available in case of disk failure. In contrast, the other RAID levels that include redundancy invariably require reading the other disks in order to reconstruct the data from a failed disk. On the other hand, the fault tolerance in RAID 1 comes at the cost of a higher degree of redundancy, therefore requiring more storage capacity. RAID level 5 is quite popular overall, as it strikes a balance between the read and write performance, storage efficiency, and fault tolerance. A storage subsystem can be defined as a separate external entity with a certain level of onboard intelligence that contains at least two storage devices. With external, we mean external to the server or servers. In what follows, we kick off with an overview and classification. We then discuss DAS, SAN, NAS, NAS Gateway, iSCSI, and storage over IP. Enterprise storage subsystems emanate from the insight that the management cost of storage tends to exceed by far the sheer cost of purchasing storage hardware. In addition, the often perceived rigor of purely centralized data centers resulted in the need for more flexible distributed storage architectures, which still offer centralized management capabilities. Modern enterprise storage subsystems often involve networked storage, which is connected to high-end servers by means of high-speed interconnects. The network topology provides for transparent any-to-any connectivity between servers and storage devices, and in this way functions as a black box of storage. It combines large storage capacity with features such as high-speed data transfer, high availability, and sophisticated management tools. The main characteristics of state-of-the-art enterprise storage subsystems can be summarized as follows. Accommodate for high-performance data storage. Cater for scalability and in particular, independent scaling of storage capacity and server capacity. Support data distribution and location transparency. Support interoperability and data sharing between heterogeneous systems and users. Reliability and near continuous availability. Protection against hard and software malfunctions and data loss as well as abusive users and hackers. And finally, improve manageability and reduce management costs through centralized management of storage facilities which may themselves be distributed. We can classify the technologies for realizing storage subsystems according to three criteria: the connectivity, the medium, and the I/O protocol. With connectivity, we refer to the way in which the storage devices are connected to processors and/or servers. This is illustrated in a figure. Direct attach refers to storage devices with a one-to-one connection between server and storage device. Network attach refers to storage devices in a many-to-many connection with the corresponding servers by means of network technology. With the medium, we refer to the physical cabling and corresponding low-level protocol to realize the above-mentioned connectivities. In other words, to transfer data between storage medium and server. We discriminate between the following main technologies: SCSI, or Small Computer Systems Interface. This has been a standard to connect storage devices to servers and/or processors for decades, although in several incarnations. SCSI is currently mainly used for high performance and high capacity workstations and servers. The SCSI specification involves two elements. On the one hand, a command set to communicate with storage devices, and on the other hand, specifications for a low-level protocol and cabling to transfer SCSI commands and data between servers and storage devices. It is the latter that is relevant in this medium category. The command set belongs to the I/O protocol category discussed hereafter and can also be combined with other cabling. Ethernet. This is the long-standing standard medium for local area networks, LANs, and sometimes wide area networks, WANs, mostly in combination with the Internet Protocol stack TCP/IP. It is not specifically aimed at storage-related data transfer. Fiber channel, FC. This is a more recent medium, developed specifically to connect high-end storage systems to servers. Originally, it was based on fiber optical cable, hence the name, but nowadays it also supports other cabling such as copper wire. Depending on the vendor, different topologies are possible. The I/O protocol denotes the command set to communicate with the storage device. With this high-level protocol, the transported bits take the meaning of I/O requests exchanged between servers and storage devices. In this context, we discriminate between the following. Block-level I/O protocols. The I/O commands are defined at the level of requests for individual blocks on the storage device. The SCSI command set is widely used for this purpose. Originally, SCSI I/O commands could only be exchanged over SCSI cabling, but nowadays other media such as fiber channel and Ethernet can also be used for transporting SCSI commands. File-level I/O protocols. The commands are specified at the level of requests for entire files on the storage device. The protocol is device independent as it is situated at file level and therefore not impacted by the physical block position of the data on the storage device. Widespread file-level I/O protocols are network file system (NFS), originating in the Unix and Linux world, and common internet file system (CIFS), but also known as server message block (SMB), mainly popular in Windows environments. Also, some internet application protocols can be positioned under this denominator, in particular HTTP, Hypertext Transfer Protocol, and FTP, File Transfer Protocol. With DAS, the storage devices are directly connected to individual servers. A block-level I/O protocol is used. Servers communicate with storage devices by means of SCSI I/O commands. As to the medium, different options are possible. This could be a standard SCSI cable, but the SCSI commands can also be exchanged over point-to-point fiber channel or, although less common in this setting, an Ethernet cable. Each storage device is connected to a single server or, for the sake of failover, to two separate servers. In this configuration, no network is used for traffic between servers and storage devices, although obviously servers and clients can be connected to a standard IP network for LAN or WAN functionality. Failover means switching to a redundant or standby system in case of malfunction of the primary system. A DAS setup is the simplest and least expensive solution. However, it doesn't offer out-of-the-box capabilities for centralized storage management and sharing unused disk capacity across servers. Even more important, this approach is reasonably vulnerable to hardware failures in servers, storage devices, and cabling, since there's only a single path between individual servers and storage units. In case of failure of any of these components, part of the data may not be reachable. Here you see a DAS illustrated. In a SAN setting, all storage-related data transfer occurs over the dedicated network. Again, servers and storage devices communicate by means of a block-level I/O protocol, such as SCSI commands. But now, the network provides an any-to-any connectivity between servers and storage devices. Most often, fiber channel is used as medium, with different possible network topologies. Ethernet-based SANs are possible as well, but these are discussed in a separate section. Apart from the separate storage network, clients and servers can communicate over a standard IP-based LAN or WAN. A SAN is superior to DAS in terms of availability, given the any-to-any connectivity between servers and storage devices and the redundancy in access paths given the network setting. The latter also facilitates data sharing, hence reducing unnecessary data redundancy. Note that data redundancy is not mitigated entirely because redundant copies are still needed for reasons of availability, but redundancy is not needed for the sake of providing the same data to multiple unconnected servers. A SAN is typically also the best solution in terms of performance. Other advantages are the flexibility and scalability of being able to make separate decisions about adding servers and storage devices to the SAN. These decisions are much more intertwined in a one-to-one setting. Given the network technology, a SAN is also able to bridge larger distances than direct connections between storage devices and servers. In addition, the connectivity between the devices offers possibilities for storage pooling and centralized management. On the other hand, SAN technology is still rather complex and expensive, with the added burden of ever-evolving standards of hard and software. Hence, the SAN approach is mainly beneficial to larger organizations with sufficient expertise and financial resources. Here you can see a SAN illustrated. NAS is essentially a quite straightforward and inexpensive way of organizing storage facilities into a network. A NAS device is often called NAS appliance because of its relative simplicity. It is a specialized device for file storage which can be plugged straightforwardly into a TCP/IP-based LAN or WAN, hence the medium is Ethernet. To put it simply, a NAS device can be considered as a stripped-down file server which consists of an integrated combination of a processor, operating system, and a set of hard disk drives. Yet, in contrast to a real server, there is no keyboard or screen, and the operating system is stripped down to the bare minimum necessary for its sole purpose, serving files to the network. In this way, a NAS appliance is not only less expensive than a full-blown server, but there is also less complexity in the hardware and software that may cause failures. Also, in contrast to a SAN, NAS devices are accessed through a file-level I/O protocol such as CIFS, NFS, or sometimes HTTP or FTP. The NAS offers a file system to the network with file requests being translated by the NAS's internal processor into SCSI block I/O commands onto the actual hard disk drives. This conversion is transparent to the outside world. From a client perspective, a NAS behaves similarly to a general purpose file server. There exists a very extensive range of NAS devices. Some have very limited functionality apart from basic file serving, whereas high-end NAS devices offer more advanced features such as automatic backup and recovery, support for RAID, email-based error notifications, remote administration, etc. The main advantage of NAS technology is that it offers very flexible, relatively simple, and inexpensive facilities to add additional storage to the network in a plug-and-play fashion. In this way, it is good for file sharing on the network, possibly between different servers and platforms. Yet, performance is in most cases lower than with a SAN setup. This is because all storage-related traffic passes over the standard LAN or WAN rather than over a dedicated network. Also, the file-level access makes life easy when the main aim is to share unstructured files on a network. On the downside, the indirection of file-level access being translated into block-level access is less efficient, especially to high-end DBMSs, which often prefer to directly access the raw storage devices at block level, hence bypassing the file system provided by the operating system or NAS device. Here you can see a NAS illustrated. A NAS Gateway is similar to a NAS device, but without the hard disk drives. It consists of only a processor and a stripped-down operating system. On one side, a NAS Gateway can be plugged into a TCP/IP-based LAN or WAN, whereas on the other it can be connected to external disk drives. This connection can be realized by either DAS or SAN technology. In this way, the NAS Gateway receives file-level I/O requests from servers connected to the LAN or WAN and translates these into SCSI block I/O commands to access the external storage devices. In comparison to a normal NAS device, a NAS Gateway offers more flexibility as to the choice of disk drives, as well as more scalability since it is not confined by the physical boundaries of the NAS box. More importantly, it allows plugging an existing disk array into a LAN or WAN, hence making its content accessible to the entire network. In this way, the same disk array becomes accessible by means of both file-level I/O through the NAS Gateway and by means of block-level I/O via DAS or SAN. As such, a NAS Gateway can yield a hybrid NAS-SAN environment, where an existing SAN can also be accessed on file level from a LAN or WAN through the NAS Gateway acting as a front end. Here you can see a NAS Gateway illustrated. iSCSI, also called Internet SCSI, or with a more general term, storage over IP, offers a setup that is similar to a SAN, but instead of fiber channel, the much more familiar Ethernet is used as a medium. SCSI block-level I/O commands are packaged and sent over a TCP/IP network. This network can be the normal LAN or WAN or a separate network dedicated to storage, but still based on familiar LAN technology and protocols. This results in a SAN-like setup, although iSCSI can also be used for a direct connection between server and storage device. iSCSI solutions sit somewhere in between iSCSI solutions sit somewhere in between SAN and NAS. They allow for block-level disk access, like SAN, but they are Ethernet-based like NAS. Overall, they provide for a lower cost alternative to SANs, since the Ethernet hardware is often less expensive than fiber channel. It is also possible to reuse existing LAN components in this way. In addition, Ethernet technology is much more familiar to most than fiber channel and less prone to incompatibilities and/or teething problems. For that reason, iSCSI is particularly popular in small and medium-sized organizations in comparison to SANs. On average, iSCSI can also cover larger distances than FC-based SANs, but typically it is a bit slower than fiber channel. Here you can see iSCSI illustrated. To summarize this section on enterprise storage subsystems, this table summarizes the defining properties of each technology. Note that this overview provides the main categories in a continuously evolving landscape and that many vendors offer variations and/or hybrid approaches as well. We conclude this chapter with a brief discussion on business continuity. We start with an introduction. Next, we define contingency planning, recovery point, and recovery time. We discuss availability and accessibility of storage devices. We then continue with availability of database functionality. We conclude with a discussion on data availability. In the context of database management, business continuity can be defined as an organization's ability to guarantee its uninterrupted functioning despite possible planned or unplanned downtime of the hard and software supporting its database functionality. Planned downtime can be due to backups, maintenance, upgrades, etc. Unplanned downtime can be due to malfunctioning of the server hardware, the storage devices, the operating system, the database software, or business applications. A very specific and extreme aspect of business continuity is an organization's endurance against human or nature-induced disasters. In that context, we speak of disaster tolerance. An organization's measures with respect to business continuity and recovery from any calamities are formalized in a contingency plan. A primary element of such plan is the quantification of recovery objectives, considering an organization's strategic priorities. The recovery time objective, RTO, specifies the amount of downtime that is acceptable after a calamity occurred. The recovery point objective, RPO, specifies the degree to which data loss is acceptable after a calamity. The consequences of RPO and RTO are depicted in this figure. The aim of a contingency plan is to minimize the RPO and/or RTO, or to at least guarantee a level that is appropriate to the organization, department, or process at hand. A crucial aspect in this context is to avoid single points of failure, as these represent the Achilles heels of the organization's information systems. With respect to database management, the following points of failure can be identified: availability and accessibility of storage devices, availability of database functionality, and availability of the data itself. In each of these domains, some form of redundancy is called for to mitigate single points of failure. We discuss the respective domains in the next sections. The availability and accessibility of storage devices was already covered when discussing RAID and enterprise storage subsystems. For example, network storage, in addition to other considerations, avoids the single points of failure that a DAS setup implies with respect to the connectivity between servers and storage devices. In addition, the different RAID levels not only impact the RPO by avoiding data loss through redundancy, but also the RTO. For example, the mirror setup in RAID 1 allows for uninterrupted storage device access, as all processes can be instantaneously redirected to the mirror drive if the primary drive fails. In contrast, the redundancy in the format of parity bits in other RAID levels requires some time to reconstruct the data if the content of one drive in the RAID configuration is damaged. In terms of availability of database functionality, the first simple approach is to provide for manual failover of DBMS functionality. This means that a spare server with DBMS software is standby. However, in case of a calamity, manual intervention is needed, initiating startup scripts, etc., to transfer the workload from the primary database server over to the backup server. This inevitably takes some time, hence pushing back the RTO. A more complex and expensive solution, but with a much better impact on the RTO, is the use of clustering. In general, clustering refers to multiple interconnected computer systems working together to be perceived in certain aspects as a unity. The individual computer systems are denoted as the nodes in a cluster. The purpose of cluster computing is to improve performance by means of parallelism and/or availability through redundancy in hardware, software, and data. Availability is guaranteed by automated failover, in that other nodes in a cluster are configured to take over the workload of a failing node without halting the system. In the same way, planned downtime can be avoided. A typical example here are rolling upgrades, where software upgrades are applied one node at a time, with the other nodes temporarily taking over the workload. The coordination of DBMS nodes in a cluster can be organized at different levels. It can be the responsibility of the operating system, which then provides specific facilities for exploiting a cluster environment. Several DBMS vendors also offer tailored DBMS implementations, with the DBMS software itself taking on the responsibility of coordinating and synchronizing different DBMS instances in a distributed setting. A last concern in the context of business continuity is the availability of the data itself. Many techniques exist to safeguard data by means of backup and/or replication. These techniques all have a different impact on the RPO and RTO. Of course, also here, a tighter RPO and/or RTO often comes at a higher cost. We present some typical approaches. Tape backup. With tape backup, the database files are copied periodically to a tape storage medium for safekeeping. Tape backup is still the least expensive backup solution. However, it is a time-consuming process, so the frequency is necessarily somewhat lower, which has a negative impact on the RPO. Therefore, tape backup is often combined with other precautions, such as maintaining multiple online copies of the log file. Restoring a backup copy from tape onto a functional database server after a calamity is a time-intensive process as well. Tape backup thus has an equally negative impact on the RTO as on the RPO. Hard disk backup. The process of making and restoring backups to or from hard disk is more efficient than tape backup because of the device characteristics such as better access times and transfer rate. This has a positive impact on the RTO and possibly also on the RPO. Still, as to the latter, the frequency of backups not only depends on the characteristics of the backup medium, but also on the infrastructure where the primary copy of the data resides. For example, the workload of the source system and the possible performance impact on the latter may be an important factor to determine backup frequency. As already discussed earlier in this chapter, storage networks taking the burden of data and backup-related traffic from the LAN and from the servers can be a solution here. Electronic vaulting. Creating backups is key to business continuity, but in most cases, it is also essential to safeguard the backup copies at a remote site at sufficient distance from the primary site to avoid them from being involved in the same incident or disaster. A simple but error-prone approach here is to manually transport the offline tape backups to the remote site. A more efficient technique is electronic vaulting. Here, backup data is transmitted over a network to hard disk or tape devices at a secure vaulting facility or at an alternate data center. This process can be largely automated. Replication and mirroring. The techniques mentioned thus far are all asynchronous approaches. Backup copies of the data are only created periodically. Therefore, whatever the frequency, there's always a certain amount of data loss, and the RPO will never coincide with the moment of the calamity. To avoid data loss altogether, synchronous techniques are needed, maintaining redundant copies of the data in real time. Two closely related terms in this context are replication and mirroring. Some authors consider them to be synonyms. Some define them in slightly different ways. We refer to mirroring as the act of performing the same write operations on two or more identical disks simultaneously. Mirroring is always synchronous. The most well-known implementation of mirroring is rate level 1. Replication is the act of propagating data written to one device over a network onto another device. This can be done synchronously or semi-synchronously or asynchronously. Many SAN and NAS implementations, but also DBMSs and dedicated replication servers feature replication facilities. Synchronous replication and mirroring provide near real-time redundant copies of the data and thus cater for a very strict RPO. Of course, the trade-off is the cost of the solution, but also the performance impact that real-time replication may have on the source system and sometimes the network. Asynchronous replication is more flexible in this respect. Disaster tolerance. To guarantee a tight RPO and RTO under any circumstances, remote data replication is needed to an actual second data center at a sufficiently distant location. The data can be replicated over a dedicated network such as a WAN or over public lines. The same considerations play with respect to synchronous versus asynchronous replication, with the addition that asynchronous replication is less sensitive to network latency, which may be an important factor given the distance. The remote side should be fully operational, and in that case, it may also handle some workload to relieve the primary side, or at least be able to become fully operational in a very limited amount of time. This means that not only up-to-date data should be available, but also DBMS functionality should be up and running or at least standby. In some implementations, both the primary and the backup DBMS are conceived as nodes in a cluster that spans both the primary and remote data center. We refer to this as a stretched cluster. In this way, failover but also load balancing, for example, can be managed efficiently between the primary and backup facilities. Of course, at each individual site, there is still the need to mitigate single points of failure by providing redundant storage devices, as well as servers, network components, power supplies, etc. This figure provides an illustration of a stretched cluster with primary and remote site. Transaction recovery. As a final remark, it must be stretched that replicating the data alone not always suffices to guarantee data integrity in case of calamities. Also, the transaction context must be preserved. For example, suppose disaster strikes in a bank amidst a set of database operations where money is withdrawn from one account and about to be transferred to another account. Even if the data files themselves were replicated synchronously from the primary site to the remote site, the remote database is not necessarily aware that a transaction was going on where money was already retrieved from one account but not yet deposited on the other account. This information, which is vital to the consistency of the database, is what we call the transaction context. If the overall data replication is coordinated at DBMS level and not at operating system or network level, then typically the transaction context is also transferred between the DBMSs. One popular technique here is called log shipping. It means that the log file, which keeps account of ongoing transactions, is replicated between both DBMSs. The remote DBMS can use this log file for transaction recovery, or in other words, to restore the context of the transactions that were going on at the primary site. In this chapter, we dealt with a broad range of aspects pertaining to physical database organization. First, we presented the building blocks of physical databases such as tablespaces and indexes. We explained how the presence or absence of different index types affects query performance, according to an optimal access path as determined by the query optimizer. We also focused on several types of physically realizing join operations. In the final parts of the chapter, we returned to the hardware aspects of storage, discussing technologies such as RAID, SAN, and NAS. We concluded with an overview of some database-related concerns with respect to business continuity. If you want more information, happy to refer to our book, Principles of Database Management. See also the website at the bottom of my slide.